Good morning, good afternoon, and good evening. Hope that you are all doing well and staying safe. Here is Mariam Shref, a senior petroleum engineering student at the Lebanese American University. Welcome to the first lecture of our online course, Applications of AI in Petroleum Engineering, presented by a distinguished guest speaker, Dr. Ahmed Farid Ibrahim. Now, the applications of AI has been very active lately, where it has been providing AI-based solutions to various problems in petroleum engineering. Therefore, I advise you to give your full attention to Dr. Ibrahim's lecture today. Dr. Ibrahim is an assistant professor at the Department of Petroleum Engineering at King Fahd University of Petroleum and Minerals since January 2021. He worked as a teaching assistant at the Department of Petroleum Engineering at Cairo University for more than 3 years. He has more than 10 years of diversified international experience, including working for Advantech International Company as a geomechanical engineer and Apache's North America Unconventional Resources region as a senior reservoir engineer. Dr. Ibrahim earned his PhD in December 2017 from Texas A&M University. And finally, his research interests include reservoir modeling and simulation for conventional and unconventional reservoirs, production and well performance analysis, shale gas and oil resources assessment and characterization, CO2 sequestration, and finally, AI application in reservoir engineering. Welcome, Dr. Ibrahim, and thank you for joining us. And we are pleased to have you with us today.
Thank you, Mariam, so much for this nice introduction.
And on a final note, don't forget to register for this course on Google Classroom. And if you have any question related to the technical content of the presentation, please feel free to drop it down in the Q&A section. Now, without any further ado, Dr. Ibrahim, the mic is yours.
Thank you, Mariam. Assalamu alaikum, everyone. Good morning. Our webinar, inshallah, or our course will be about application of artificial intelligence in petroleum engineering. As a petroleum engineering, I will not go in deep in the programming of the artificial intelligence. We are applied science, so I will use the available, like there is a lot of machine learning techniques, modules already available. So I'm not gonna show how to program it, but I will show you how to apply this techniques, this machine learning or this artificial intelligence into your problem. So the outlines for the webinar, inshallah, including today and the next lectures, are gonna be first introduction about the artificial intelligence. I will start with a very simple definition, just to know what the AI is. Then the type of the artificial intelligence, supervised and unsupervised artificial intelligence techniques. And I will give some summary about examples of the AI techniques that that's already available for you to use, like ANN, neural network, supported vector machine, and so on. So this one here is basically an introduction about the AI. Then the next sections here is to apply this one here on the problem. I focus on a petroleum problem, but for sure you can use it in any other problem. So I will start to define the methodology to do that and the model development. The methodology basically consists of data analysis. And in the data analysis, I will prepare my data to have a best model to improve the model performance. So the data analysis is going to include univariate statistical analysis and the multivariate statistical analysis. And the second part of the methodology is the model development. I will show you what is the process of developing the model. Yes, the code is available, but there is a certain procedures you need to follow in order to have a model that can be used to predict any parameter as a function of other features. After we develop the model, I'll go through how to evaluate this model, how to validate it, what is the parameters that we can use in in order to evaluate this model and in order to see if this performance is good enough to be used in the future or not. Finally, I will give more applications about these techniques in petroleum engineering. I will give some case studies in the application of the AI in the drilling engineering, reservoir engineering, and the production engineering. So let's start with the introduction about the AI. As all of you know, AI have been used in our life in different aspects, different issues. For example, in order to filter your emails, like the anti-spam filters, Google ranking, and the web page. So this one here actually provide a customized recommendation. Like another one here, like if you are doing some shopping in Amazon, or you are based on your watching the movies that you are watch, you're gonna have some recommendation based on the AI in case of like Netflix or Amazon. So an example for this machine learning here, as I said, is web page ranking, photo tagging, or anti-spam filters. So machine learning or artificial intelligence, basically it is the study and the design of intelligent agent that can be used and allow any machine to learn from experience or perform a human-like tasks. So basically, the artificial intelligence look or use the data and try to learn by itself without specifying or specified programming. Like I don't program the machine how to solve it. No, I give the machine a set of data, and the machine start to learn from this data in order to solve the future problems. We have two types of artificial intelligence. The first one is a supervised machine learning or a supervised learning. The second one is unsupervised learning. Supervised learning, from its name, it is supervised during the learning process. So basically, we will teach the computer on how to learn and then in the future, the computer will use his learning to predict. But in the unsupervised learning, we just give the computer a set of data, and the computer start to classify or make some clustering on this data. So for more details about this one here, the supervised learning technique, it is the most common machine learning techniques, the most available. And it means that we give the algorithm a data set with a correct answer. So basically, we give the machine learning or the tool, we give it like the input, and here is the output. Okay, and then we ask the machine learning to learn from this one here based on the input. This will be your output, and later on, after he learned from this data set, he will start in the future for any set of input data, he will calculate or predict the output. There is two different. The supervised learning can be used to solve two different problems. The first one is the regression problem. The second one is the classification problem. So what's the difference between the regression and the classification problem? So for the regression problem, your output here is a continuous value. That means you have, like, for example, you are predicting the permeability as a function of other set of parameters like porosity, gamma ray, or density of the rock. You are trying to predict the permeability. Permeability has a continuous value, let's say from 0.1 millidarcy up to 1,000 millidarcy. So it is continuous value. It can have any value in between. Okay, we can use infinite number of features to make the regression. So the input parameters can be as many parameters as we can. And is this one here, later on I'll show you how to judge the number of input parameters, how to select the most accurate or the most good input parameters that will fit the problem in order to predict the output. As I'm giving here as an example, one example of this one here is to predict the permeability. This is like an example for the regression problem. For the classification problem, the output is a discrete values. Discrete values like mean, It is 0, 1. Like you don't have a continuous in between. We may have 2 or more classes of answers, so it can be like 0, 1, 2, 3, or whatever. We can use infinite number as same as the regression. The input parameter for the classification can be infinite number of input parameters. And for this one here, an example for it is prediction of the formation lithology. Like if I have a set of, like if I'm drilling some well, I want to know what is the lithology of the formation. So the lithology will be sandstone, limestone, clays, like carbonate, or whatever is the lithology is. So it is just a class. So there is nothing in between. Okay, so this is the difference between the regression and the classification. Classification, white or black, or whatever the color is. The regression, you have a certain number in between, like minimum and maximum. So for you to remember, we have two types of the artificial intelligence, supervised and unsupervised. The supervised can be used to solve two different problems. The regression problem here to predict a continuous value. Classification problem to predict a discrete value of the output. An example for the machine learning tools or the artificial intelligence tool, we have artificial neural network, ANN, function network, FN, support vector machine, adaptive neural fuzzy interference system, which is the ANFIS, random forest. We have so many tools, like we have decision tree, we have like KNN. So we have many tools that can be used to make our to use the AI in to solve the problem. Yes, each technique here, each tool has its own process for learning and then for the prediction, but at the end, the same procedures will be followed. Like you prepare your data, you feed your model the training data, and then you ask the model to predict the data in the future. So for the ANN, for example, it's basically trying to mimic the human biological neural network to learn and make decision. So similar to your input, like in for your human biological neuron, for example, it's basically what's coming from your inputs, like the touch, the feeling, what you see, what you smell. So this is basically your input, and then your neuron start to make some functions, some weights from this inputs, having certain functions, and then we use this one here in order to at the end to know what is the output. So basically, the element for the ANN, input layer, hidden layers, and output layers. So the input layer, this is basically what you input to your model, like in case of permeability prediction, for example. You input for him, for the model, the porosity, gamma ray, the density at a certain permeability. Okay, so at a certain depth, you have the input and the output. And then you feed the neural network these input parameters, which is the input layer. Then the module here start to make some connections between this input with a certain weight and certain biases, and then have another layer. Then this layer here start to have also some connection between the output with a certain weight and certain biases also, in order to have the output layer. And your output here is basically what you have as a result for the model. The second one is the ANFIS. ANFIS is doing the same, but here you have the concept of fuzzy logic with the neural network. So your input, you make some fuzzification for it, okay, some randomization for this one here, and then you do your weight and biases in order to do the calculation, and at the end you make a deep fuzzification for the output in order to have your results. So the ANFIS is basically combine the fuzzy logic and the neural network in order to have a hybrid intelligent technique to improve the ability to automatically learn and adapt. So the ANFIS same as the neural network, but for the input and the output, we need to do some falsification or some data analysis, some data manipulation in order to improve the learning ability of the model. For the support vector machine, similarly, it is a supervised learning approach that carry out transformation of an input data set into a high degree dimensional, n-dimensional. So it basically takes the input data and convert it into high degree dimensional feature space, and use this one here to learn or to teach the model. And after that, use this learning process in order to predict your output at the end. Similarly, the function network here, function network, it's a strong predictive tool and can be used also for prediction or classification based on the technique. So it can be used for regression or classification problem. So here you have a function associated with each neuron. So the neuron, like similar to the ANN, you have a certain function like polynomial function, Gaussian function. It's associated with each neuron, not just a number. No, it's a function. And then use this function, okay, to keep and to make the model to learn more. And this function here depends on the nature of the data set. Function network uses some multi-argument functional models so that they don't need the weight and the biases. So similar to the ANN, we need weight for each neuron and the biases in order to match the parameters. But this one here, it's instead of the weight and the biases, it uses the function. This function can be polynomial, Gaussian. There is so many different functions that the function network depends on it. Another one here, the random forest or decision tree. So random forest is basically also can be used as a classification and regression technique. It's basically a summation of, look, it has many decision tree. For each tree, here it uses the input parameter with a certain way based on the logic in order to reach the output. So the difference between the random forest and the decision tree, it's just one tree. Start from your input based on certain logic, you reach it to your output. In case of random forest, you have many, you have a forest of trees, you have many trees, and for each one has its own input, its own set of inputs, and the output depends on it. And at the end, we do some voting based on which one is working well. So what I want to let you know or just to discuss with you here, it's not how to build these tools. There is so many codes for the random forest machine like ANN, function network, AMPHIS, support vector machine in a different language. You can see it in Python, you can see it in MATLAB, in our language. So I'm here not to discuss how to program this one here, but how to use it. So what I'm gonna do inshallah today and the next lecture is how to use this available codes in order to predict your parameters. So for the second class of the AI, which is unsupervised learning, and as I said, this one here is not common. We basically feed the model a set of input parameters, like we give it a set of data. We don't tell it, this is one here is the input or this one here is the output, and the model start to make some cluster based on the nature of the data. And this one here is not that common, so I will not focus on it during my lecture, inshallah. So this is like the clustering is like similar problem for the clustering, like the Google News. You will see that in a certain area here, this is for movie news, for example. This one here, just political news, and so on. So this is one of the cluster problem. So we just give the model all the data set, and based on the nature of the feature, the machine learning start to just categorize it, just make a cluster from it. Okay, so this is like a quick introduction for the AI in order to be familiar with the terminology, just to be familiar with the terminology of each machine learning when I talk about it during my lecture, inshallah. So for the methodology, And in the methodology, as I told you, I will show you, I divided it into two parts. The first one is data analysis. I'm preparing my data to be used for the machine learning before I feed the model the input data and the output data. So the first one is data analysis. The second one is model development, and at the end, the model evaluation and the validation. So for the model, basically this is an example for the flow charts that you can use to build your machine learning model. First is the data analysis. You collect your data. For example, you want to predict the permeability. So the permeability can be predicted, for example, from a different well logs. What is the available well log for you? Make some cleaning and some transformation. I will show you what is the cleaning, what is the transformation, and what is the classification, inshallah, in the data analysis. After that, we divide your data into two data sets, testing and training data set. Randomly, we split the data randomly to testing and training with a different ratio. Like, for example, we can use 60% of the data as a training to train the model, and 40% to test the model, or we can increase the training data set to 70, testing is 30, this one here 80 or 20. This ratio here depends on the performance of the model. Then we, for each model, like random forest, ANN, support vector machine, whatever is the model, there is some hyper parameters. These parameters here we can adjust, like what is the learning rate for this model, what is the number of neurons that you're going to use for the ANN, what is the number of hidden layer in the ANN in order to improve the performance. So this one here, we can select this model's parameters. Then we run the model for the training. Then we evaluate the model by comparing the outputs, the actual data and the data from the model. Compare the performance of it. If it's good, if the performance is good, that's fine. If not, we go adjust the model parameters. And at the end, once the model training is very good, we go for the testing. We test the model. If the test pass the criteria, then you have the model to predict any data in the future. If not, you need to adjust your splitting ratio. So for today, inshallah, I'll focus on the first part here, which is the data analysis or the statistical analysis. And basically, the statistical analysis, we can divide it into univariate problem and multivariate problem, or bivariate. So multivariate, this is bivariate or more than two variables. So for the univariate problem, basically, like before we go to this one here, in any problem, like as I said before, you are predicting your permeability as a function of different gamma, well logs. So in the univariate statistical analysis, I'm dealing with each feature or each parameter as it's one problem. I do the analysis for the permeability by itself. I do the analysis for the porosity. I do the analysis for the gamma ray, and so on. For the bivariate problem or the multivariate problem, I'm trying to get a relationship between the input and the output. Is there a relationship between the porosity and the permeability? What is the shape of it? Can I improve the relationship or between these two parameters or not? And for the input parameter itself, is there a relationship between the gamma ray and the porosity? Can I remove one and just use one, and the porosity can give the same effect as if I use the gamma ray and the porosity or not? So this is basically what's the difference between the univariate statistical analysis and the bivariate statistical analysis. So for the statistical analysis for the univariate one here, we need to define three different parameters or three different categories. The first one, to measure the location of your data. So this one here includes defining the mean of the data. You have like 1,000 data points. You need to know what's the mean for this parameter, like what is the average porosity, what is the average permeability, what is the average gamma ray, what's the median, what's the mode. and what is the maximum of the data point, and what is the minimum value in the data point. For measuring the variation, how the parameter vary within your data set. What is the range of your data set? Like the porosities vary from 1 millidarcy to 1,000 millidarcy, or it vary from nanodarcy to a millidarcy. Similarly, the variance, the standard deviation. What is the shape of the distribution? Is the distribution is a Gaussian distribution? It is log distribution, or what is the shape of the distribution? Because this one here will affect your model development. So for measuring the location, I will not go like through how like the calculation of it. I'll just go quickly on this one here. This is like based on your mathematic background. So for the mean, it's basically arithmetic mean, the summation of the data point divided by the number of data. So we call it the mean or the expected value. The mode is basically the one or the property value with the high frequency. So let's say this is the distribution of your data. So this is the distribution mean, this is the frequency in the y-axis versus the property. So the mode is basically the property value at which we have the high frequency. So let's say you are dealing with a porosity for this one here, and the porosity is vary from minimum value of 0.1 millidarcy up to 1,000 millidarcy. But most of your data point, the high frequency is at, let's say, 10 millidarcy. So that's mean here is your mode. For the median, this is the point at which at 50% distribution. So if you arrange your data point like from the low value to the high value, after 50% of the data point, what is the value of the porosity or the permeability here? Okay, this is the median. So this is how to calculate the arithmetic averaging, or how to calculate the median. So the median is basically the value of the property, okay, divided by 2. If it's odd number, so this is like the value of the property at n plus 1 divided by 2. So if you have, let's say, 99 data point, okay, after you arrange it from the high to from the low to the high, the median basically gonna be the value of the permeability or the property at the value of 50. If your number of data point is even, like let's say you have 100 data point, if you have 100 data point, the value of the median basically gonna be the value of the permeability at 50 plus the 51 was divided by 2. This is to measure the location of your data set. To measure the variation basically the range. So the range is maximum minus the minimum. For the standard deviation, for example, standard deviation, it describes the overall variation relative to the arithmetic mean. So it's basically, so this one here is this one here is the variance, the property minus the mean, which is this one here, the arithmetic averaging, to the power of 2, make a summation and then divide it by n. So this is basically the arithmetic average for the variation between your value and the mean. If you take the square root of the variance, this will give you the standard deviation. Okay, the standard deviation is very important because it shows you what is the distribution of your parameters. So usually in a Gaussian distribution like this one here, the mean, median, and the mode usually have the same value if it's a Gaussian distribution. The standard deviation here, if you moved one standard deviation, okay, from the left of the mean and the right of the mean, you're going to have around 68% of the data point will fall in this area. And if you take 3 standard deviation to the left and 3 standard deviation to the right, you will count for 99% of the data. So this one here is very important in case of like smoothing or removing the outliers. So let's say you have like 1,000 data point, and your data point, most of it is vary from 0.1 up to like 100 millidarcy, but you have few data points outside this range. Like you have like 3 data points, one is 0.001 millidarcy and another one is like 1,000 millidarcy. So this one here can be outliers. So we can use the standard deviation technique in order to eliminate these outliers. So once you have your data set and you have it like that, you calculate the standard deviation, and then you select the data point that is within 3 standard deviation only. Using this one here, you're considering 99% of the data set and you are removing any outliers, a very low permeability or a very high permeability. So using this technique here, this will help you a lot in developing the model, will make it converge faster and the accuracy of it will be much higher. So why we are doing this one? Why we are calculating the location, why we are calculating the variance, and how this one here, how we take this location or the variation into consideration in order to build our model. So let's say we have a problem like this, similar example. We want to predict the permeability as a function of the porosity, the density of the grains, gamma ray, okay, or any other logs here, let's say the resistivity, for example. If you look to the distribution or the values of each parameter, the permeability, for example, it vary from 0.1 to 50 millidarcy. Gamma ray, it's vary from 100 to 300 API. Density vary from 1 to 2.9 gram per cc. The porosity vary from 0.02 to 2 fraction. Look closely to this one here. See this one here, the variation in this one here is like in the degree of 0.1. This one here, the variation vary in rank of 1. This one here vary in 100. And this one here also in like a rank of 10. So if you're gonna use this one here as it is on the machine learning, this will make the convergence of any machine learning tool or some of the machine learning tool very difficult. Plus, it's like mixing, like this one here, machine learning is like mixing a fruit. Okay, if you want to do like a mixed fruit juice, for example, if you want to use apple here and here strawberry, if you said, okay, I will use 5 strawberries and 5 apples, what's gonna be the result of your juice? For sure, it will be most of it just apple, because of the size of the of your apple. Okay, so what you need to do is scaling this one here to the same scale. You need to scale your input to the same scale. So at the end, the results will be depends on the importance of this one here, not its scale. So if we back to this one here, if you did your machine learning technique, if you applied you use this data to feed your machine learning technique, so by logic, the machine learning will see that the variation in this one here, like it's 200. It has much more variation in order to make this one here, in order to predict the permeability. So it will give more weight for the gamma ray, even though the porosity may be more important than the gamma ray in order to predict the permeability. Okay, but the variation in this one here is very small, so it will give it much more less weight. So the first thing, once you know the location and the variation of your data, is to see is your data input is in the same scale or not. Okay, and we know this one here from the location and the variation of your properties. So the scaling, we use it to avoid deceive superiority. Okay, we don't want to give this one here more weight than the other. Okay, we want to have the weight based on the importance, not based on the scale of it. Second, it will give you the opportunity for the machine learning to converge much more faster comparing if we used the unscaled parameters. So how we can do the scaling? The most common techniques to do the feature scaling, the first one is the normalization. The second one is the standardization. So for the normalization is basically you use this equation here. You convert your parameters, your porosity, for example, to a normalized porosity based on the minimum and the maximum value for your data set. So you're basically the normalized property will be x, which is the property, actual property, minus the minimum value divided by the range. Using this one here, you will see that your range of the property will vary from 0 to 1. So the property here, the minimum value will be 0, where x here is the maximum, it will give you 0. And minimum, when your x here is the x minimum, so x minimum minus x minimum, this is the 0. The second technique of the scaling is the standardization. The standardization is basically depends on the mean and the standard deviation of your data. So the standardized x or the standardized property is basically the actual property minus the mean divided by the standard deviation. So in this one here, it moves the whole curve, the whole data set to have a 0 mean and 1 standard deviation. So the standard deviation in this data set here will be the unity, and the mean is basically will be 0. So let's see how the shape of the data will change with the different scaling. So let's say this is the original data. You have, let's say this is a porosity. Okay, it's vary from very small values. This is a grain density, and this is this is the permeability, and this is your gamma ray. Okay, so this is the original data set. With the normalization, what happened? It make a scale for the whole data set to be from 0 to 1. Okay, from the 0 to 1, but the mean for each data set is different, but it is still within the range. It's from 0 to 1. Okay, the change in the property is the same for all the data. In case of standardization, with doing this scaling technique, we basically move the data to have almost 0 mean, and the standard deviation is almost 1, but the range for this data is different from one to another. But it will not changing like from 0.1 rank to like 100 rank. Like it's not changing that much. It is still within the same range. Like this one here from -3 to 2, for example. So at the end, which one you're gonna use? Which one you're gonna use? Okay, so are we gonna use the scaling always as the scaling will affect or not? So there is some machine learning that is sensitive to the scale of the features, like the ANN, KNN, the supported vector machine. Any technique that has or built or like its training or prediction, it depends on having a relationship between the parameters of each other. Like it takes the first input and put it a certain weight for it, and combine it with the second input. Okay, put this one here with another weight in order to predict the output. Like ANN, KNN, function network, ANFIS, all this technique here, it depends on the scale of the features. So with this one here, it's important to use one of the scale technique like normalization or the standardization. Some techniques that is based on the logic, such as the decision tree or the random forest, just the logic, it doesn't feel the calculation. Just like it take like we start from here. This is your input. If it's high, it will take this route. If it's low, it will take the other route. Okay, so it's but just logic, not about weight or biases. So this one here, in this case here, this one here will not affected by the scale of the features. So you scale the your data input or you don't scale it, it will not affect it. There is no correct answer to when to use normalization over standardization. Okay, it depends on the nature of your data. It depends on the nature of your data. So run your model you're using the raw data, run your ANN with your raw data without scaling. See what is the performance. Like does it converge faster? What is the error at the end? And then run the model with the scaled data. You can do normalization using x minus the minimum divided by the range, or use the standardization technique in order to do the scaling. Okay, so what I used to do in my work, I usually do normalization, then run the model, see what is the performance, what is the behavior. If it's satisfied, then I just use it. If not, I'll go with the standardization and maybe compare it with the raw data, especially if I'm using it with the ANN, KNN, or any of these techniques. Okay, so this is regarding the feature, regarding the location and the variation of the property. What about the shape of it? Like, what is the distribution? How the distribution of the data look like? Is your distribution look like this one here? This is a normal distribution where most of your data here, the frequency of it is high at the middle point of your data, middle value of your data, or it is something like this. There is some shift, like your data is a little bit more shifted towards the right. Here you see that most of your data at the lower end of your property. So in this case here, in case of normal distribution, you will see that the mean, median, and mode is almost close to each other. And as I explained to you before, this one here, the distribution will depends on the standard deviation. Like if it's a normal distribution, within 3%, within a 3 standard deviation in the right and 3 standard deviation on the left, you will have around 99% of your data set. So another shape for your distribution can be something like this one here. It is called positively skewed distribution, where your data, okay, most of it is towards the lower end of your value. As I said before, for permeability, for example, it's range from 0.1 to 1,000 millidarcy. Okay, but most of your samples, most of your actual data is basically toward the lower end, which is a 0.1. So you see that most of your data points from 0 to, let's say, 100, but from 100 to 1,000 don't have that much of the data point. Or it can be something like this, negatively skewed distribution, okay, where your data is going towards the upper end. Okay, most of your data is at the higher end of your property. So knowing this one here, okay, once you know this one here, you'll see how to to deal with your data. If you used such a data like this one here or this one here, when your model try to fit your parameter or make your regression, it's basically you have like a function, object function. Okay, we want to minimize this error between the actual and the calculated from the model. So this function here is basically the summation of the error for along all your data. So if your data is skewed to the right or skewed to the left, that means some of the data range here will be weighted. So here, for example, the values at high, the model will be more accurate at high value of this property. In this case here, the property, the model, the AI model will be more accurate in this one here because it's creating much more data. But here the error will be high at the data where we have less frequency. So usually we are trying to have a normally distributed data here. So you have your error is like distributed, okay, in order to have the best model. So how to do that? We do some data transformation in order to convert your data from a skewed data point or data distribution into somehow normal. It will not be a perfect normal distribution, but it will be close to the normal distribution one. So one of the most common technique to do the transformation is the Box Cox transformation. It's basically you take a power of your property by a certain value. Okay, this value here, it's range from -5 to 5. Okay, when you take the power for your property from -5 to 5, it will move the skewness from the left here to the middle or from the right to the middle. Except if your parameters, like here, you tried -5, you didn't reach the best distribution. You used -4, -3, but you still not able to move your data point to centered. Okay, at once you reach to close to 0, if you used to the power of 0, this one here is it's 1. Okay, that's it's not acceptable. So instead of using the property to the power of 0, we use log or len of the property. Okay, so this one here is we call it the Box Cox transformation, in order to convert the data from the log scale distribution into sorry, from the non-normal distribution, like positively skewed distribution or negatively skewed distribution, into a normal distribution. So an example for this one here, let's say I have a set of data. We have a porosity and the permeability. The porosity, for example, this one here, it vary from, let's say, 2 up to 3 point something %. Okay, so the porosity is the range of it, like from 2 to the 3. But if you look to the distribution for the porosity, this is the distribution of it. Basically, see, very normal distribution. Most of the data distributed, most of the data, the higher frequency of the data is basically close at the mean of the data. But if you look to the permeability, it ranges from, let's say, around 5 millidarcy up to 500 millidarcy. And if you look to the trend here of the permeability, most of your data is less than 100. See, most of your data is between 5 and 100, and only a few points at the 500 point. And from this curve here, from the probability distribution curve, you can clearly see the distribution. Most of your data, it's less than 200, and only a small amount of the data from the 200 to 500. So what we need to do in order to convert this one here to the normal distribution one? So what I did here, I take log for the permeability. So instead of plotting versus the permeability, instead of using the permeability as absolute value for the input for the model, I used the log permeability. And with using this one here, it's clearly convert this shape, this distribution from this one here into a very nice normal distribution. And we can use this one here for the model as input. So when you are predicting, like in this one here, for example, in this one here, instead of using permeability as an output for the model, no, go ahead and use the log permeability for it. One more thing here, the feature scaling does not affect the distribution, It has the same distribution, but it just move it from bigger scale to lower scale, but the distribution of it will be the same. Even here for the normalization, your permeability, if you look closely to this one here, it's ranging from 0 to 1, but if you see here, this is your mean here. Most of your data, it's toward another end, which is the lower end here, but when we normalize it, become near to the 1. So the scaling does not affect the distribution of the data, but just affected the location or where is your data. It's like in the hundreds or it's in the tens. So sometimes you need to do scaling and the transformation at the same time, or do transformation first and then do scaling, because like the transformation may reduce the scale of your data. Like for example here, it converts the scale of the permeability from hundreds into ones. So the permeability change from, instead of from 5 to 500. Now it's changing from 2 to 6. Okay, so first, what you usually do, make your transformation first, then you can do the scale if needed. And here is the plot of the permeability and the porosity after you do your transformation. It's clearly that now the range of the permeability is from 2 to 6. Okay, so this is regarding the univariate property. Now for the multivariate property or the bivariate property, it's basically we want to see the relationship between the features. So now I want to see what is the relationship between the porosity and the permeability. What is the relationship between the porosity and the gamma ray? What's the relationship between the gamma ray and the for example, the resistivity? Can I remove one of the input and this will not affect, or each of the input is independent features? Okay, so this is what we're gonna gain from the bivariate statistics. The first step to do the bivariate statistics is a scatter plot. You plot the x1 versus x2. You plot the features versus each other. Okay, using this one here, you can clearly from this one here see, yeah, there is a trend between x1 and x2. As the x2 increase, x1 increase, but it's not always. Okay, like it's not 100% increasing x2 will lead to increasing in x1. For example, if you are comparing this point here with this point here, if you are comparing this point, okay, with this point here, x1 it increased even though the x2 there is no change on it. Okay, but the general trend on it saying that x2 it's increasing with x1. In order, instead of just visualizing this one here, we can quantify it using the Pearson's correlation coefficient. So Pearson's correlation coefficient, it measures the correlation between two variables, okay? And it's vary from -1 to 1. -1, there is a strong negative relationship between the variables. 1, there is a strong positive relationship between the variables. How to calculate the correlation coefficient? This is a equation for it. It's a function of the property, the first variable and its mean, the second variable and its mean. This is basically the number of the data and the standard deviation for each variable. So the sign indicates the direction of the trend. Okay, it's negative or positive, and the absolute value shows the strength of the relationship. If it is absolute value close to 1, that means there is a strong relationship. If it's close to 0, that means there is no relationship. So for example, something like this, the red one here, strong relationship between x and 1, but in an inverse direction, reverse direction. As the x2 increase, for sure x1 will decrease. See, the correlation coefficient equal to 1, there is a strong relationship between x2 and x1. Then with decreasing the correlation coefficient, so the data start to be a little bit scattered, but still there is a good correlation between x2 and x1. Yes, with increasing the x2, x1 will increase with 80%. If you look to this one here, x2 and x1, there is no relationship. Okay, so for example, if you are predicting, if you plot this one here, and you have here, this is your permeability, for example, and here this is your resistivity. Okay, so there is no relationship between the resistivity and the permeability. That means you can exclude this one here from your inputs. You can just ignore this one here. Do not use it to predict the permeability. There is no relationship. And something like this, x1 and x2. If you are using, for example, the in a petroleum industry, you can get the porosity, for example, from the neutron, or you can use it or get the porosity from the sonic, for example. If you plot the neutron porosity versus the sonic porosity and you got your correlation like that, 1, there is no need to input both into the model to get permeability. Only 1 is more than enough. This one here will accelerate the convergence. Plus, so the correlation coefficient, we do it between the output and your input, and between your input and between the input with each other. Okay. This is another example here for the correlation coefficient. For example, the light concentration versus the brittleness index. Okay, is this rock here easy to frack or not? So if your light concentration increased, your formation is much more ductile formation, so it's difficult to break it. So the brittleness index decrease. If you compare it with the quartz concentration instead of the light, you have a positive correlation. Okay, so once we have the correlation, is it like, can we just use like you have the correlation coefficient between the porosity and the permeability is 0.75. Yeah, there is a good correlation between the porosity and the permeability. But can I do some transformation in the data in order to improve this one here? So I feed the machine learning a clean, nice data that it would be easy for it to find the relationship between the permeability and the porosity directly. Can we do that? So we can do it. So as the CC increase, if we can increase the correlation coefficient between the input and the output, okay, if we can increase the correlation coefficient between the input features and the output value in the AM model, the model accuracy will increase and it will converge much more faster. So yes, you need to do more work in your data before you input it to the AI. So for example here, when I converted the permeability, instead of just using a permeability, I converted to log permeability. Compare between the correlation coefficient in this case here and in the previous case. If you compare just the absolute value of the permeability versus the porosity, in this formation here you have 0.75, and in another formation you have 0.92. But if you compare it with the log permeability, your correlation coefficient is 0.98. Very strong correlation between the permeability and the porosity. So once you feed it to the machine learning, it will converge fast and it will give you very accurate results. Another example here. For example, if you have like a certain property and this is the output, the relationship when you plot both together, it has this trend here. If you calculated the correlation coefficient for this data here, it's 0.11. It's very small correlation, as if there is no relationship between the X and Y, which is not reality, because correlation coefficient give you the linear relationship, linear correlation between the two variables. So in this case here, it will be good to separate your problem into two different problems. You solve it until here for a variable for the property from 0 to like 12, you use this model. And when your property is higher than this, you use another model. From the petroleum industry, for example, a good example for this one here is the, for example, the oil formation volume factor. Okay, so this is oil formation volume factor. Sorry, it's supposed to be like this. Oil formation volume factor versus the pressure. So this is not, this is supposed to be the pressure. So it has this trend. The oil formation volume factor, it has this trend here. Okay. With increasing the pressure, oil formation volume factor is increasing until it reaches a certain point. Once it reaches this point here, the trend completely changes. It starts to decrease. This one here for the petroleum industry, we know it as the bubble point here. So if you have a problem to predict the oil formation volume factor from a set of data, don't use the whole data and feed it to the model. No, classify it, categorize your problem. Instead of you have one problem, make it two problems. For pressure less than the bubble point, use this model, and for pressure higher than the bubble point, use this model. Doing that, the correlation coefficient in each one is very high. See, this one here is 0.94, and this one here is 0.9 from 0.11. So you have to work, you have to work your data, look to your data first, plot it, see how to deal with it. Another parameter that we can help us to judge our data is the ranking correlation coefficient. The ranking correlation coefficient, it is the same as the correlation coefficient, same as Pearson correlation coefficient, but it take out the effect of the outliers. So for example, if you have, see this set of data X and Y, but you have one point here, which is the outliers at very high X and a very high Y. So if you calculated the correlation coefficient, it will give you a very high correlation coefficient, as if, so the correlation coefficient for this one here is 0.65 correlation coefficient for the data here with the outliers. If you put this data here in Excel and fit it, it will give you very nice R square. Okay, the correlation coefficient is basically the square root of the R square. Okay, but this is not the reality. This one here is just an outlier. Maybe it's an error. So we just need to remove it. Okay, and if we removed it and we calculate the rank, you will see that there is no relationship between X and Y. Actually, the correlationship may be not decrease, maybe it will go the other way around. So let's say if your data is like that, okay, but you have one point here. See, the correlation coefficient will give you a trend like this. Even though the relationship has a negative trend, due to the presence of the outlier, the correlation coefficient is negative value, has a positive value. So how to take out this outlier effect? We use this one here, we call it the rank correlation coefficient. So we are not dealing with the actual value of the property, we are dealing with its rank. What is the meaning of its rank? So let's say the porosity, we have the porosity is 0.1, 0.2, sorry, excuse my writing, I'm using the mouse here, so 0.5, 1, okay. Let's say this is the permeability, 10, and you have how many points? 1, 2, 3, 4, 5, you have 5 points. So this is the actual value. So the rank of it, you basically order your data, arrange your data from the low value to the high value, and then just give it a number for each one. So this is the rank number 1, rank number 2, rank number 3, and so on until rank number 5. You do the same for all the property, and then you deal with the rank instead of the absolute value. So if you have an outlier of like 1,000 millidarcy, its rank will be just 6. Okay, so having a rank instead of the actual value here, it will exclude the effect of the outlier from the calculation of the correlation coefficient. Okay, but if you don't have an outlier, the correlation coefficient, Pearson correlation coefficient will be similar or give you the same result as the rank correlation coefficient. Plus, so this is the example here. You have like this 50 data point with an outlier with a correlation coefficient give you 0.65. If you just remove this one here, it will give you the correlation coefficient of 0.087. If you did this calculation but using the rank, you have your correlation coefficient is almost the same. Okay, when you compare the rank of X versus the rank of Y. So rank correlation coefficient is more robust form of the correlation coefficient than using the Pearson correlation coefficient. Okay, so this is an example, this one here to summarize the statistic analysis for the univariate and the bivariate one. You can do this one here using different any software, MATLAB, Python. I did this one here using Python. So basically, in this scattered plot, you just plot the cross plot between the property, the output, which is here, for example, this one here, maximum horizontal stress, versus the input, which is this one. Okay, you just plot the data. You can see here there is a nice trend here between these two properties. Here, the correlation coefficient is very small. This one here has some trend. and so on. In addition, it gives you the distribution of the data. This data here, somehow it has some skewness to the right. This one here, it's good, not bad, and so on. This one here has some skewness to the left, so you need to do some transformation on it. If you look to the correlation coefficient, this map here show a correlation coefficient between your output, which is this one here, versus the input parameters, which is this one. This one here is 0.45, 0.62, 0.5, 0.4. This one here is negative 0.3. This means the output here has a negative relationship with this parameter, positive with this, and the strongest correlation coefficient with this parameter. This means here, this one here is much more important to predict the output. Plus, so similarly, this is between the input parameter with each other. Like for the sake of examples, like if you have one of these parameters here and your correlation coefficient is 1, that means you can exclude this one of this input from the input data set. How to do the calculation for this, like the statistical analysis? You can do it using Excel, or you can do it using Python. For example, I will show you just an example for the Excel sheet. I'll not go through the calculation. So for example, this one here, I hope you can see my Excel sheet here. So this is the data for the thickness, for example, of the formation. It's so easy. You can just calculate the minimum, maximum, mean, median, mode, and the skewness factor for all your data set. The range basically is minimum minus the maximum. Using the frequency function in Excel, you can have a histogram or the distribution of your data, something like this. You do this here one by one, okay, in order to have the distribution or to have the statistical analysis for each one. If you want to know the correlation coefficient between two parameters, let's say we have the first parameter here in B column, this one here is the second one. If you want to know the correlation coefficient, there is correlation coefficient function built in the Excel. You can use it called correl, and then you compare these two here together. Okay, so this is the correlation coefficient between this one here and this one here. Sometimes you, instead of Excel, you can use Python. So the good thing about Python, it is like there is a very there is a lot of built-in equation, built-in function on it. You can just call it. So after you load your data, you can just call this describe function, and it will give you all the statistical analysis for all your variables, like the count of your data points, the mean, the minimum, the standard deviation, the maximum, and all the quartiles. In addition, you can use it to plot the correlation coefficient or calculate the correlation coefficient. So this one here is basically the correlation coefficient between the parameters with each other, or plot the scattered plot for your data. I will not go through this one here, but it's available online. Just Google it, how to calculate such in Python. This one here is called the scattered plot. How to calculate the correlation coefficient in Excel, and inshallah it will be easy to have it. Any questions? So this is, I will not go more behind after this one here. I will stop in the data analysis, and next time, inshallah, I will go through the model evaluation. That's it, and I'm ready, inshallah, to answer your questions. So, Mariam, are you gonna?
Okay, thank you, Doctor, for this informative session. Now we'll be addressing some questions. So the first question is that if someone is interested in machine learning applications in the petroleum industry, but he's facing difficulties in finding data sources that are related to petroleum engineering, where can you suggest some resources of petroleum data?
Yeah, that's true. Data is one of the problem, like in machine learning, because machine learning it depends on the data availability. But there is some data that you can find, like I think there is Norway, I think Norway. There is website related to the Norway oil and gas fields. There, it has a lot of data. It's open. You can download it. There is, like, if you are dealing with production data, drilling info, or any of these websites, there is something called I don't remember the website, but there is a website with the production data for Texas, for example, Texas State, Texas Roadhouse. It's called the Texas Roadhouse website. It has so many production data from different, like, gas, condensate, oil, plus the literature. Like if you want to have, like, let's say, absorption of the certain gas on a rock. There is so many experiments in the literature related to this one here. So what you need to do is go ahead on the literature, see what's the paper that has this data, and then start download, categorize, have the property with for each one, and start working on it. Other than that, you will this is the only way to do it, or you have a connection to a certain company if you are dealing with a certain project, for example.
Okay, thank you. Another question is that, is univariate analysis a good approach to showcase a trend, knowing that in general there are many factors that influence a certain quantitative property?
So you are absolutely true, but it is a step. As you see here, I did it step by step. So I do it first once the univariate, just to see each parameter by itself. Then I take it another step here to see the property with the second one, the property with the output, the property with the another input, and then see, do I need to do more transformation or not, and so on. So the univariate is like a step by step. I start from, I don't want to make it more complex. I don't want to jump to the model development. It is better if you take it one by one, like on steps. So once you have it like that, if there is any mistake, you'll be able to go back and redo it or check it. So univariate problem and then multivariate problem. This is what I believe it's better procedures to do or to develop your model.
Okay, thank you. Now, the last question for today. Do you recommend any book related to artificial intelligence and machine learning in the petroleum industry?
I think there is so many textbook related to this one here, related to the machine learning in general and machine learning in a petroleum industry. But I believe there is a nice one. I remember it is machine learning in reservoir engineering. I like this paper. It's like a review paper. You can Google it. It's a journal paper. I don't remember if it's in One Petro or Science Direct, but go to Google, look for the application of artificial intelligence in reservoir engineering. Very nice paper. But for sure, it will not give you this basics. It will jump to the application. For this one here, you need not AI in petroleum. You need a statistical data analysis, any of the data analysis book, in order to prepare your data for the machine learning. So machine learning can be applied to any industry, oil and gas, or any other industry. The same procedure will follow: data analysis and then build the model. For data analysis, use your like the textbook related to the data science. For the AI in petroleum, there is so many published paper, just to give you an idea which one is related to which. Like permeability, can we get the permeability from the porosity from the gamma ray? Can we get the wettability from as a function of the mineralogy, function of the salinity of the formation, and so on, just to know the physics behind the parameters, not just applying blindly the data. Also classify it or categorize it into two parts. First one, know your data from the data science point of view, and then the physics behind your data from the petroleum point of view.
Okay, thank you very much, Doctor, again, and thank you for your time. I hope you all enjoyed this session today. Please don't forget to join Google Classroom for this course and submit the quizzes and the final exam before the assigned deadlines. To clarify, you will only be able to receive a certificate for this course if you submitted the quizzes and the final exam with a passing grade of 70. Now, for those who have missed the lecture or want to rewatch it, this session has been recorded and it will be uploaded soon on Arab Guru's YouTube channel. Now, to highlight, we are still having 3 more lectures for this course, which are going to be every Monday, 2 p.m. Egypt time. So basically 13, 20, and 27 September. Now that's all for today. With that, I want to wish you the best of luck and have a nice day.
Thank you, Mariam, and thank you all for attending. Assalamu alaikum.